And shut your laptops and all that other good stuff. Please put out your name tags, shut your laptops. Uno. Top shut, folks, please. Thank you. All right, let's begin. We're going to decide what was the last thing we were discussing. Okay, so we were discussing recurrent neural networks. We were discussing the stability of recurrent neural networks. And Eli, what was the very last kind of model we discussed?
The very last kind of what?
Model.
The very last kind of model.
Exactly. Okay, someone's been noticing. Thank you. So we're going to continue. Here's where we were. We saw in general that recurrent structures can be trained by minimizing the divergence through these time series can be modeled through recurrent neural structures. And these can be trained by minimizing the divergence between the sequence of outputs and the sequence of desired outputs. Because you're modeling sequences, the losses are also defined over sequences. And this is the real challenge, because when you're modeling sequences, the output sequences can be arbitrary. The notion of error can be very complicated, as you'll see in a bit. So the challenge is, how do you define this divergence? And how can you use this divergence to actually train the network? Now, here are various variants of neural networks. The standard neural network is the figure to the left. It's just an MLP. You have some input shown by the pink boxes, which goes into your hidden layers. And then finally, you have the output shown by the blue box. Each input generates an output. The kind of model that we saw in the last couple of classes was the one to the right, where you have a sequence of inputs. And corresponding to each input, there is an output. But then you can have other structures, like the first one to the left. So this is where you have an entire sequence of inputs coming in before you take a decision about it. Or, so for example, if you're doing isolated word recognition, you'd have to see the entire input before you decide what was spoken. Or you can have something like the figure to the right. Now, this is more complex. The output is not synchronous in time with the input. You don't have one output for every input. What you have is intermittent outputs, but the sequence of outputs is order aligned with the input. What do I mean by order aligned? So a typical example is, say, speech recognition. And you might have some speech signal going in. And so if you were to, the person might have said, hello, good morning, right? So where has the word hello, where can you actually identify the word hello when it's ended? So that would be right here. Where can you identify the word good? That would be right here. You can identify the word morning when the word morning has ended. There's a sequence to the outputs, and the sequence to the outputs is related to the sequence of inputs. So the portion of the input, the word hello, occurs before the word good. So the portion of the input that corresponds to hello will occur before the portion of the input that corresponds to the word good. So the input and output are order aligned, but they're not time synchronous. And this is the problem that we're actually going to be spending the next couple of classes over. But then you can also have other kinds of structures, like the one to the left, which is typical in machine translation, where you must see the entire input before generating the entire output, or something like the figure to the extreme right, which is very popular these days, language modeling. You give it a prompt, it goes ahead and generates the whole thing thereafter, right? So let's look at some of these models. This is a conventional MLP, where for every input, you can have an output. But this can also be used to model sequences of inputs. There would be no recurrence in this case. Every input vector is going to be analyzed by the network, and then you'd get an output corresponding to every input. Because each input is being independently analyzed, the output at any time t is not influenced in any manner by the processing or the output at any other time t prime. Nonetheless, if you want to use these to model sequences, you can still sort of use it to capture the sequential structure of the data through the loss. And in this case, you'd be defining the loss between the actual sequence of outputs generated by the network and the desired sequence of outputs. Now, the one restriction is if you wanted to use this to train your network, the loss must be differentiable. The loss must be differentiable with respect to every single output of the network, because if you cannot differentiate the loss with respect to the network outputs, you cannot back propagate anything, right? So in this setting, here you do have a one-to-one correspondence. You don't necessarily have a one-to-one correspondence between the actual output of the network and the desired output, but you could assume one. And if you assume that there's a one-to-one correspondence between the desired Ys and the actual Ys, then the loss, the divergence that you define, can be simplified. The actual divergence would be the divergence between the target sequence and the actual output sequence. But if you have a one-to-one correspondence, and furthermore, if you assume that the divergence between the target and the actual outputs is the sum of the divergences computed at each time, then the derivative of this total divergence with respect to the output at any given time is simply going to be the derivative of the local divergence at that time, simply because the total divergence is being computed as the sum of all of the local divergences. So this is something that we're going to exploit. But in the case of just using MLPs to model recurrent structures, the time series nature of the data can be captured through the loss. And if I break the loss down as being a sum of losses at individual times, it simplifies the math, but it also breaks down the structure, the sequential structure that we are assuming, right? Anyway, here's the first part. Okay, time's up, guys. Is anybody on Zoom?
Yes.
Hello.
You guys answer both questions. What's the answer to the first question?
True.
Second one.
True.
True.
So you can actually use conventional MLPs to model sequences, provided you capture the sequentiality through the loss. But then when you break the loss down as being the sum of the losses at individual times, this assumption kind of breaks down, right? Now, let's look at the second type of model where you have what I'm calling time synchronicity. At each time, for each input, there is a corresponding output. There's a one-to-one correspondence between the output and the input. So this is the kind of network that you might want if you are performing part of speech tagging of text. Every single word in your text has a part of speech tag. Now, the precise part of speech tag that you want to assign to it depends on how it is being used in the text. This is not always unique. And so you would have to look at what is happening on either side. And typically in text, you'd also want to look at what followed the word in addition to what preceded it. So you'd want to have some kind of bidirectional network to perform the part of speech tagging. Even though the network is bidirectional, you still have a one-to-one correspondence between each word and the output. In determining the tag for the word, you might have looked to the right, you might have looked to the left, but the word itself does get assigned a tag. And so you get a one-to-one correspondence between the output and the input. So you have time synchronicity. And once again, I'm going to assume that the networks are unidirectional just for convenience, but always keep in mind that it's perfectly valid to assume that you have the entire input sequence before you begin analyzing it. So your network could be bidirectional. So here you would be given some, for each input, you'd be given the actual input for each training instance and the desired sequence of outputs, which might or might not be the same length as the input. And the network is going to generate a sequence of outputs. So for a problem like part of speech tagging, the desired output is going to be exactly the same length as the input. There's going to be a one-to-one correspondence. But in other problems, you might not find this, right? But for time synchronous problems of this kind, when there's an output for every single input, okay, I should wind back a bit. For time synchronous problems in particular, when you have an output for every input, you will have a desired output for every input. Nonetheless, the loss is going to be defined over the two sequences. And as a first step, if you want to perform backpropagation, you want to be able to compute the derivative of this divergence, the loss, with respect to every one of the outputs of the network. So you would need to be able to compute these terms, the derivative of the overall divergence with respect to the output of the network at each time. And furthermore, even though your loss is ideally being computed between two sequences, in a problem like part of speech tagging, for instance, where each word is going to be either right or wrong, you can actually decompose this divergence as being the sum of the individual divergences at each time. And then thereafter, if you want to compute the derivative of the overall divergence with respect to any particular output, you just need to compute the derivative of the local divergence with respect to that output. And if you're performing classification tasks, the most common divergence to be used is the Kullback-Leibler divergence, which is analogous to the cross entropy. It's identical to the cross entropy to be within an additive constant. So this, in fact, for the rest of the explanation today and Thursday, we're going to assume that we're using the KL divergence. And any questions? I don't think there was anything particularly complicated so far, right? Thumbs up. Okay, Ji, what's the answer?
A and C.
A and C. Does everybody agree that A and C are the correct ones? So there's only one output corresponding to every input when we are speaking of time synchronous recurrent neural networks. The networks can be bidirectional, and the divergence between the true and the desired outputs can have an additive contribution from every single output, right? So this is what we're going to build on. So let this be burned into your heads. In the case of time synchronous networks, you're going to have one output for every input. And although the divergence is ideally defined between sequences, you can, in principle, also define a divergence, which is the sum of the divergences at individual outputs. And so what we will often do in problems like these, where you might have a loss or a divergence between the two sequences, which is very complicated and doesn't seem to have any kind of clean structure, we will actually try to decompose it, to modify it in some manner so that it falls into this bucket, because then things become tractable. Anyway, let's move on, right? Let's consider this problem, where the many-to-one problem, where you have an entire sequence of inputs before an output is generated. So this could be, for instance, in question answering. Someone asks, what's the color of the sky? And then you have to answer blue. You're not going to answer blue before you hear the final word. It wouldn't make sense if you don't know what it is you're trying to know the color of, right? So you'd see the entire input before you generated the output. Or if you were performing speech recognition for isolated words, you'd have to see the entire word, segmented out word, or a wake-up word recognizer. And then at the end, you're going to generate an output. So easy enough, right? Inference is easy. I'm going to be given an input sequence. I would analyze the input sequence using my network. The input sequence can be arbitrarily long. There's no, so it's, although my figure always shows these 3 columns, it doesn't mean that you only have 3 columns. Different inputs might be different lengths. So the number of columns is going to depend on the length of the input sequence. And then when the entire input sequence has been analyzed, at the final input vector, you are going to generate an output. But then this is a recurrent network. Every column is identical to every other column, remember? So that means because you're basically using the same network to keep analyzing forward in time. So if every column is identical to every other column, and I'm only reading the output at the final input, what is happening at the other inputs? Can anyone tell me? What happened to the other inputs? Why is there no output at those times? Pardon me?
There is an output, but it is just going to the next layer.
There is an output, but remember, we just ignore it. That's all we are doing, right? Because every column is identical to every other column. It's going to be generating an output at every time. We just pretend it doesn't exist. Now, if I'm training the network, I have an actual output at the end of the input, and I'm going to have a desired output. So if I'm performing phoneme recognition, at the end of the sequence of inputs, it might say, aha, this is the phoneme E. Then I look at my training label, and it says it's the phoneme A. So now I can compute the KL divergence between the actual and desired outputs. And the derivatives of that divergence can be propagated backwards through the network, and we know exactly how to perform backprop. You wouldn't have any difficulty writing the backprop rules for this, right? Is this making complete use of the input, or are we losing something? Yeah.
There are outputs for like the previous token, but we didn't use it.
Exactly. So we're pretending there's no useful information in these places, right? But if I'm performing phoneme recognition, if I'm saying ah, then it's ah at every single time, right? For me to pretend that all of these outputs had no relevance doesn't make sense. I'm throwing away useful information. So what would make sense for me to do would be to just replicate my target output at each time, and then use the derivatives from all of these time instants. What have I done in this process? I've actually taken this was an asynchronous problem, right? I didn't have an output for every input. I converted it to a synchronous problem. And now we know how to deal with synchronous networks. Yes, Advait?
But for the color of sky type of...
Thank you. Right. So I can define my divergence everywhere. And to answer Advait's question, there are situations where it doesn't always make sense. I can't say that the word answer must be blue as soon as the word color has been output. So it makes more sense to say I'm going to have a weighted sum of these losses at each time. And you can always choose the weight. And in the case of the color of sky, you're saying the weight is 0 at the first 2 times and then 1 at the final input, or depending on how the evidence is built up, you can always modify these things. But the point is that once you get past the weighting, you've converted it to a time synchronous problem, right? So everyone with me so far? This is easy, right? Nothing complicated about this. Now we're going to get into the more complicated one. This is the, yeah.
Like for the color of sky like situation, can we have a specific token, output token like silence or something like that? And we enforce the model to only output silence before like the final.
This is text. There's no silence.
Something similar.
You could. I mean, there are other engineering solutions, but the concept is clear, right? So now, let's look at this problem. This was what I said was a speech recognition problem, right? Now, do you see a relationship between the figure to the right and the figure to the left? What is it?
Blocks of many to one.
Blocks of many to one, right? So this is, in this problem, you're given a sequence of inputs, and you want to asynchronously generate a sequence of outputs. Now, this, as Denise just mentioned, is just a concatenation of many blocks of, several blocks of the many to one. But how does this complicate issues? Anyone? We don't know the length of the individual segments. All you're given is the entire input sequence, right? And so we don't know if the network is actually generating outputs at every time. We're just ignoring some of these and reading some of these. How do you know which ones to read? There's no clear answer. We have to come up with some mechanism to decide, right? So which of all of these outputs are the real outputs? I mean, which are these that represent definitive occurrences of a symbol? There's no a priori information about it. So in order to do this, we have to go back and look at what the network is actually doing. Now, what is the network? When I draw these figures over here, each of those blue boxes, is it actually just a symbol?
No.
What is the network output?
The distribution.
It generates a probability distribution over all possible symbols at each time. You do this in your homework, right? You get probabilities, you pick the most probable one. And so even here, if I were performing speech recognition, I'd have a set of phonemes, and at each time, it's going to generate the probabilities for every single phoneme in my vocabulary. And so what I actually get is a vector of probabilities at every time, something like this, right? Now, when I perform standard classification using a neural network, what exactly am I doing? The network is generating the posterior probabilities for every one of my classes given the input. You're given some input X, and it's saying, what is the probability? Given this input X, what's the probability that this is a cat? What is the probability that this is a dog, right? And then you pick the one that was most probable, that most probable class given the input. That's how the network operates. We can use the same principle here as well. But then, just looking ahead a bit, here is the issue. I'm given some input speech, right? And what are all the possible outputs over here? What are all the here?
The number of different in terms of like the number of probability distributions we can have?
So how many classes do I have?
Okay.
So here is the thing. This sequence could just be my phoneme A, right? It could be A. It could be A, and so on. It could be A, B. It could be B, A. It could be B, A, and so on. How many possible sequences do I have to evaluate to decide which is the most probable? Every single, as many sequences as you can fit within the length, right? Potentially infinite. In your standard classification problem, the number of classes is predetermined. If I'm performing image recognition, here are these 1,000 classes of images, pick one. If I'm performing speech recognition, you just vaulted into an entirely different domain. The number of classes depends on the length of the input, and it's exponential in the length of the input. Because the number of different sequences that you can possibly have, it can have any sequence of phonemes, right? Any sequence of words if you were doing word recognition. So now you have a problem where you cannot explicitly enumerate every single class and pick the class that was most likely. Is that making sense? Right? So then what can we do? We're going to need some kind of heuristic, right? There's no way you're actually going to go out and find every class and find the probability for each class so that you can pick the most likely class, because classes are symbol sequences and there can be an exponential number of them, potentially an infinite number of them, right? So, yeah.
Professor, aren't we detecting the last phoneme like of a sequence?
If I give you a 10-second segment of speech, how many different phoneme sequences can I fit within 10 seconds?
Worth of 10 seconds.
Yeah. Right, that's going to be 10 raised, it's going to be of the order of 10 raised to 100 or something completely absurd.
So even in the many to one example, we're returning a sequence of phonemes, right?
So in the many to one example, I may have just 50 phonemes in my vocabulary, or 100,000 words if I'm doing word recognition. Here, the number of classes is finite and deterministic, right? There are 100,000 entries that I'm getting a probabilities for in the blue box. I just pick the most likely. The moment I go from there to this, the number of classes just blew up in an exponential manner. And that's the challenge, right? Make sense to everybody? So, okay. So how would I go about this? Now this is where we actually jump into heuristics. So what we want to do is find the most likely symbol sequence. There are all of these potentially infinite possible symbol sequences. Not infinite maybe, but an exponentially large number of symbol sequences. And from amongst all of them, I want to find the one symbol sequence which is most probable, and I don't even know the length of the sequence. I have no idea how many sequence symbols there are in the sequence. And I have to find it based on analyzing the input. So can someone give me a greedy solution, a cheap solution? Yeah.
You find a high enough probability, and that's the.
How do you know high? How do you define high enough?
Threshold.
Threshold. You're going to have to evaluate all of those guys, right? How do you even begin evaluating them? How many of these sequences do you evaluate? You cannot hypothesize and then compute the probability. It just becomes too expensive. We'll get to that later, but the cheap solution would be for me to just pick the most probable symbol at each time. And so when I pick the most probable symbol at each time, what I did was to generate a time synchronous output. But the sequence that we're looking at is not time synchronous. I could just merge all of these guys and pick the symbol at the end. And I say, okay, this symbol sequence, I think the symbol sequence is whatever, GF feed, right? What would be a problem with something like this?
It does not exist in reality.
There's no way for me to distinguish between, two Fs and a single F, right? Because they're just going to become one long sequence of Fs. And so you have an issue, number one. And number two, this can be meaningless. What does it mean? You can impose external constraints. Say, I'm only going to look at sequences that represent valid words in my dictionary, but the whole thing still gets very complex. Yes, Akshay.
Can't we do this that we evaluate a priority distribution where if we see if a particular class, let's say X0 predicts a phoneme, then we can create a probability distribution that if this is the most highly predicted phoneme, this is the probability of the words or the phonemes that can follow it.
We'll get to that later, right? So, yeah, we'll get to it. Anyway, in general, we're going to refer to this process of looking at an input and generating a candidate or a potential answer to the question, what sequence of symbols does this represent? So this is going to be inference. It's going to be called decoding, okay? Now, what we just did over here was suboptimal. What did we want to do? We wanted to find the most likely symbol sequence. What did we find? Did we find the most likely symbol sequence? What did we find? We found the most likely time synchronous symbol sequence, which is not necessarily the most likely symbol sequence, right? So for example, here, how do I keep misplacing my chart? If I decide that my symbol sequence is just AB and I have, say, 6 inputs, I might have found that the most likely sequence that I got was this guy, and I collapsed it to AB. But is this the only way of having AB aligned up against 6 inputs?
No.
No, right? I could have had something like this. And that too is going to be an AB. So if I want to evaluate the probability of the sequence AB, I have to consider all possible ways of generating AB or producing AB for that particular input and sum over all of these, and then pick the symbol sequence for which this sum was the largest. We are not doing that. So this is not necessarily the most likely symbol sequence. It's a greedy answer. Okay. Anyway, we've sort of partially looked at the problem of how do I actually perform inference with a model of this kind. Here's the much more difficult problem, that of training. Once we are done with training, we'll go back and look at decoding again, right? The training in the training data, the input sequence is not, or the output sequence is at most as long as the input sequence, right? And so what your training data will contain is, for each training instance, it's going to give you the sequence of inputs and the corresponding sequence of outputs. Given these and given a collection of several of these, we want to train our model. Now, here's a problem in this. If I give you a training sequence, a training instance, for example, suppose I just gave you a, did I lose my chalk again? Soon I'll run out of chalks. You should have a motor or something. So suppose I give you some input. Instead of drawing the speed signal, I'm just giving you showing you the vectors of the sequence, because you'll be working off feature vectors. And then I give you, and I tell you that this was the word yes with these phonemes. Is this enough to train my model? What am I missing?
Locations.
The locations are missing, right? So you have this business of alignment. I need to know which portion of the input corresponded to Y, which portion corresponded to A, and which portion corresponded to S. So now, if all I'm given is the identity of the phonemes in the sequence, there are many different ways of aligning those 3 phonemes against my input. So here, for example, I have several different alignments of the word but against the input. And so if you want to give me, if you want to tell me, give me a training instance, ideally I should know exactly where each of these symbols was output, right? Simply knowing the output sequence doesn't give me this alignment. And so now I have insufficient information. Now, consider the situation where somebody actually just went through the trouble of listening to each thing, marking the boundary, and giving me the alignment. In this case, how difficult is training? Would this be difficult? Nope, right? I just compute the loss at each point, I backpropagate. What else could I do? We can fill it up, right? I can assume that the same symbol occurred at each time. This is easy. Our real challenge, and now in this case, what we would have if I didn't fill things up, where's my candy cane? First I lose a chalk, then I lose a candy cane. Anyway, if I didn't fill it up, then the loss is going to simply be the sum of the KL divergences at these 3 locations. If I filled it up by repeating the symbols, the loss is going to be the sum of the KL divergences at all times, which is, okay, again, this is important. If I'm using a one-hot representation, what is the KL divergence between the target output and the output of the network? It's going to be the negative log probability of the symbol, right? Your target output is going to be, if I represent it as one hot, it's going to be something of this kind, 0, 0, 1, 0, 0. Your network output is going to be P of class 1, P of class 2, P of class 3, and so on. And your KL divergence is going to be summation Pi log Pi over Qi, right? And Pi being 0, these things won't matter. So I'll call it target I and Pi, just to stay consistent. So these things being 0, they won't matter. Here, the target value is 1. So this is simply going to become minus log P of I, just the log, negative log of the probability of the target symbol. And you can see how minimizing this is going to try to maximize the probability of the target symbol. So when I convert this to a time synchronous sequence by just repeating symbols, then all you're really doing to compute the loss is computing the negative of the sum of the log likelihoods, log probabilities assigned to every symbol in the sequence, right? Now, by every symbol in the sequence, we are we are speaking of the sequence that you get by repeating the symbols. The real challenge is that when somebody gives me labeled training data, they're not going to give me timing information. They're just going to say, here's this recording, this is the word but. And so in this case, how would you compute the divergence? Anyone? Yeah.
Maybe if you know generally how long each phenome is.
Okay, if I know how long, you're going there, you're getting there. If I know how long each phoneme is, how do I use that?
So you expect that for this set, like if you expect R to be like 0.5 seconds, then that way.
So you're guessing the alignment. Is that correct? So here's what you can do. You can guess the alignment. And then you can use the guessed alignment to compute the loss. But then maybe you're not very sure of your alignment, in which case you can say, I'm going to use every possible way of aligning this input, this symbol sequence to the input, and I can consider all of them. Let's look at the first solution. What is this business of guessing the alignment? So this is exactly what Ritu mentioned. I'd be given the symbol sequence, and then I'm going to try to take a guess as to where the symbols actually must be inserted, and then perform the usual trick of repeating the symbols through the sequence. So I can assign an initial alignment either randomly or based on some heuristic, and then I can train my network. But then my initial alignment is a guess. It's not perfect, right? But at this point, I have a network. I can use that network to go back and refine my alignment. And then so I can refine my alignment, use my refined alignment to retrain the network and keep repeating the process. The real challenge is this then. How do I refine my alignment? How do I re-estimate the alignment? For this, let's go back and look at characterizing the alignment. The alignment tells us which portion of the input aligns to what symbol in the sequence. This is basically what alignment is, right? And I can represent the alignment simply by the timestamp at which each symbol occurred. So the alignment can be just represented by the end of each of these green boxes. But then from a computational perspective, it's more convenient for me to think of it in this manner. If I convert everything to a time synchronous sequence by repeating symbols, what is the length of each sequence in my time synchronous representation? Is this making sense? The distinction between these two, right? They're strictly the same or almost strictly the same We'll get to the why the almost in the next class. All I did was repeat the symbols, right? And so I can think of this extension that I got by repeating the symbols through the duration of the input, through the duration of the segment that represented the symbol, as the expansion of my symbol sequence. So each of these 3 over here are different expansions of the word but, where I've just taken this b and t and repeated each of the phonemes so that the sequence fills out the entire input. And similarly, if I have, so there are many different ways of expanding a given symbol sequence, right? And similarly, if I give you an expanded symbol sequence, which is time synchronous with 1 symbol for every time instant, I can collapse it back to a compressed sequence by eliminating the repetitions. So an expansion would be something of this kind. You know, if I have something like but, this is an expansion. That's an expansion, which took the symbol sequence but and expanded it out to fill out 1, 2, 3, 4, 5, 6 time instants. And a contraction would take something like this. A compression would squeeze out the repetitions and compress it back to the actual asynchronous order aligned but asynchronous symbol sequence that I want. Now, a compressed symbol sequence can be expanded in many different ways. So you can, each of these represents a different alignment, right? And on the other hand, an expanded sequence, there's only one way of compressing it. Now, when I'm speaking of this problem of, so if I have this compressed sequence but, and I want to find an alignment of the but to the input, we know that there are many different expanded sequences, all of which compress to but. So what do we mean by finding the best alignment? The problem of finding the best alignment is to find which of these various candidate expansions best fits the data. You're only given the symbols b, and t, and you have to find out which of these candidate alignments best fits the data. So given a k-length compressed symbol sequence, you know, I don't know why I use this horrible example, beefy, but I've been using it for many years, so it's, you know, tradition at this time. It's very traditional for me to also get confused by this example because it's ugly. Anyway, so suppose I was given an n-length input, an input of length, say 9, and I was given this, the transcription as the word beefy with these 4 phonemes. Then the alignment problem is to find out how many times to repeat each of these symbols to convert it to a time synchronous sequence that best fits the data. I want to find, but specifically, I want to find the symbol sequence, the time synchronous symbol sequence that when compressed gives me my target sequence. And I want to find the most probable alignment because every one of these alignments has an associated probability with it. I want to find the most probable alignment. Give them 40 for this one.
You have more time.
You have 20 more seconds. That was just your warning. This was a very detailed question because I was force feeding some stuff to you. I'll wait till all of your answers are in yes.
So you
mentioned there's only one way to create the compressed symbol.
Yeah.
Like, wouldn't that be ignoring repetitions? Like,
We'll get to that in the next class. You're right. Okay, but assuming that we're ignoring that. So does anybody want to take some of these? Lakshay, is the first statement true?
Yeah.
Okay, Evan, what about the second one? No. And Eli, the third? And Giovanni? Anyone want to take the fifth? False, okay. Only the fifth one is false, right? An order synchronous symbol sequence that is shorter than the input can be aligned to the input by repeating symbols until the expanded sequence is exactly as long as the input. The alignment of an order synchronous input to a symbol sequence to an input is going to be time synchronous, yes.
Yeah, so for the inputs, if, like, for example, the speaker or whoever says the words is someone that has like a speech impediment, how does that kind of like, how do you
We're not going to make any assumptions. We don't want to be dealing with exceptions at this point, but eventually we can, right? So, but you're right. Now, a symbol sequence that is time synchronous with an input can be compressed to a shorter order synchronous input by eliminating repetitions. And so order synchronous symbol sequences are compressed sequences, yeah.
In the input, if we assume that we are given a voice sample, what does one time mean? Like, is that dependent on us? What we take as one unit?
So we've actually been working with 100 vectors per second, right? Although each vector is computed from a 25 millisecond window. In your homework, what have you been doing? So basically, we have the segment of speech, and we are slicing it out into little windows and getting a feature from it. So you'd get maybe 100 vectors per second. Yeah. Yeah.
That window size, can we change that, or is that?
No, that's up to you, right? Yes.
I'm still a little bit confused with like the point of the compression is because did you say like two R sounds is different than one? So why like kind of?
So we are not going to deal with that right now. We're going to assume that it's unique, but you're right, that is a problem because this doesn't deal with repetitions. We'll discuss how we deal with repetitions in the next class. I want to take it one step at a time, right? Not throw too much at you. So our problem now is to find out the most probable alignment given an input and the symbol sequence, right? Now, at each time, the network outputs a probability for every single symbol in your vocabulary, right? Now, suppose I was told that this was the word beefy, right? I'm trying to align the symbol sequence beefy to the input. If I simply pick the most likely symbol at each time, will I get an alignment of beefy to the input? Why not? Why are you guys lost?
Because some sequences will come up a completely different phoneme, making the alignment meaningless.
If I just pick the most likely phoneme at any time, there's no guarantee whatsoever that I'll pick even one phoneme that's in my target sequence, right? I could just get pure rubbish, yeah.
So for like the first one, how do you like?
You just pick the one that has the highest probability, that's it, right?
But like that, you kind of start off on like a bad one.
It's a problem. That's not the right thing to be doing, right? How do you fix this problem?
We can enforce it, like we only look at the output phoneme according to the.
Okay, so I just say I'm not going to look at the other phonemes, right? That's one simple trick to be using. So this way I make sure that the symbol at each time is a symbol that's actually in my word. Is this enough? Why not? I can end up with something that's completely, so here's a different way of thinking about it. Instead of saying I'm blocking everything out, I can say I'm pulling out those 3 rows corresponding to Burr, E, and Phil, and making a separate table of probabilities with it, and then just working off of it. And so now we just align on using the reduced grid. We are assured that only the appropriate symbols will be hypothesized, but if I just pick the most probable symbol at each time, although I'm going to get the correct symbols, there's no guarantee that this is the word that I want. This is not the word beefy, right? So we're getting halfway there. We haven't quite solved the problem, but we've sort of eliminated utter nonsense. What more can I do? How do I make things better? Yeah.
Do we now inherently like build in the sequentiality? If it guesses B, it can either guess B again, but if it doesn't, it can never guess B again. We just
Yes. And how will we do it?
By,
that I don't know.
Yeah.
by incorporating some kind of a dictionary basis. Which
So yeah, I mean, these guys are getting to the answer. Does anybody else want to? Yeah.
So you can either predict B, or it can predict like what is the next phoneme after B. So like in this case, it is I.
Absolutely right. And let's see how I can do this. What I'm going to do is to pull out the rows corresponding to the 4 phonemes in my target symbol sequence, beefy, right? So instead of just pulling out b, e, and f, I'm going to pull out b, make it the first row in my new table. I pull out e as the second row in my symbol table. I pull out f, it's the third row in my symbol table, and e again, and that's the 4th row. Observe that e has occurred twice in my example. So now there are 2 instances of the same row in my extracted table. This construction making sense to everybody, right? Once I make this construction, then it's very simple. Because now I can think of this table as this grid. And if I begin drawing paths through the grid from the top left corner to the bottom right corner, where I follow the restriction that I'm only allowed to go right or diagonally down, then the sequence of symbols on the path is going to be an alignment of beefy to my input. This is making sense to everybody? Yeah.
But practically in inference, you wouldn't know which phonemes to do this with.
We'll get to inference later. We are speaking of training, right? Okay. So is this making sense? Yeah.
So how would I know if I want to put E below F or B above E?
It's the word beefy. That's the label sequence that has been provided to me. Right? So B is the first, E is second, first, second, third, E again is the 4th. I'm working on training data where the label sequence has been provided. Right? And so this one, I want to constrain the first symbol in my alignment must be the top left block. The last symbol must be the bottom right block. And I want to traverse a path that goes monotonically from the top left to the bottom right. And if I do that, that means that at any point, I can either walk horizontally or I can take one diagonal step to the next row. I can't jump a row. I can only go down to the next row. I'm going to get paths of this kind. And any path of this kind is going to represent one alignment of my symbol sequence beefy to the input. But is this enough? There's one more thing that I'm missing. What is that? Can I just take any odd path? Then I want the most probable path, right? I want to pick the most probable alignment. And so I need the most probable path. How can I find the most probable path over here? I'm just giving you the grid, right?
Literally compare all the paths, right?
How many of those will I have?
Okay, that's probably expensive. Well, we have right or diagonal move for every step.
But still, if it's long enough.
There's a mathematical function for it. But
Yeah, so does this ring a bell in somebody's head? Come on, you guys are computer science folks, right?
Permutations.
Yeah? Okay. This is, I can draw the whole thing as a graph. The arrows show where you can go from any point. So if I'm in the top, I have to start at the top left box. And from each box, I can either go to the box immediately to the right or one down. What does this look like? That's a graph, right? Are you aware of any algorithms which can find the best scoring path from one end to the other? Viterbi many, right? Viterbi is just one. But let's, and for those of you who are not familiar with this, here's what we've done. We've drawn these edges. Edge scores are 1. And now each box has a probability. Remember, we pull these rows out of the table of probabilities generated by the network. So every box has a probability. And so now if I want to find the most probable path through this graph from the top left corner to the bottom right. And to find the most probable path, I need to be able to define the probabilities of a path. Every node has a probability assigned to it because it has been drawn from the table of probabilities generated by the network. And if I take any path of this kind, like the one shown in blue, the total probability of the path, every edge is going to have a score of 1, a probability of 1 associated with it. So if I just multiply the probabilities of all the nodes in the path, that's going to give me the probability of that path, right? So this is all we really need to know. I'm using this strange notation. Y subscript I superscript B means that this is at time 1 and the symbol B, right? This was the probability assigned to the symbol B at time 1 by the network. More generally, if I want to find the most probable path. If I were doing this naively, there's an exponential number of, potentially an exponential number of such paths. So we really want to find some, but fortunately, we know how to deal with graphs. And that's what we will do. We want to find the most probable path from source to sink. And we can do this using any dynamic programming algorithm. And the most popular one amongst all of you is the Viterbi algorithm, which applies in this particular case because it's a time synchronous graph, right? So at Viterbi, is Viterbi a breadth first search or a depth first search? What kind of? Go ahead, Advait. Breadth first or depth first?
Breadth first.
Why is it breadth first?
Because it goes one time step at a time and it
So at each time you're analyzing the entire breadth of the graph.
Yeah.
Right? So it's a breadth first search. Depth first search is going to go from one end to the other, then go back and search for another path going down, right? So here all paths will always be the same length. In a depth first search, the different paths can be different lengths. All the paths that you're analyzing. Anyways, getting back to this problem, here's the little trick that we will use in the Viterbi algorithm. What happens to my chalk so they wander? I'm leaving one chalk on every table. But anyways, so here's what we will do. Let's say I have this, I'm just going to draw this using nodes of this kind, right? And so suppose I have now consider the node over here, right? Suppose I have two different paths to this node. And this path has a higher probability than this path. Then is there any chance at all that this path, which acts, so again, this guy has the lower probability and this guy has the higher probability, okay? Is there any chance at all that this path will have a higher score probability than the path above? No, because when you extend a, so which means that if the best path to this node goes through this guy, then this is going to be an extension of the best path to this node, right? If the best path to this node goes through this guy, then the extension, then this must be an extension of the best path to this node. There are only two options. This node has two parents. So the best path to this node is either an extension of the best path to this parent node or an extension of the best path to this parent node. There is no other choice because you're always extending and just adding one more probability term in. So in order to find the best path to this node, all I have to do is to go through all of the parents, find which parent had the highest probability best path, and extend it, right? The best path to any node must be an extension of the best path to one of its parent nodes. And so the best parent is simply the parent of the best scoring best path. And the best path to any node is basically an extension of the best path to the best parent, to many bests. But, is that making sense? Yeah.
think I'm missing something in the bigger picture of it. So here we're like doing an alignment, like we're figuring out an alignment given a trained network, right?
Given a network.
Yeah, this is training.
But okay, but we don't know. Very initially, the network will just output.
Okay, just hold your horses for a few more minutes, and then you can ask that question once we're done with this, right? So is this making sense? This is easy, right? And so this gives me the simple Viterbi algorithm. I'm going to dynamically track the best path from the source node to every node in the graph. At each node, I'm going to keep track of what is the best parent and what is the probability of the best path to the node. And I'm just going to do this left to right, and then I'll work my way back from, and I do this forward computation from source to sink, and then work my way back to find the actual best path. So here's what I would do. Here, I've just thrown some notation here. If I have something like B phi, then I'm using the symbol R to represent the index of the row. So this is R0, R is 1, R is 2, and R is 3. So SR is the symbol in the rth row. So S0 is going to be B over here, S1 is going to be E, S2 is F, and S3 is E, okay? And the subscript T represents time. So Y subscript T superscript SR is basically the probability assigned to the symbol in the rth row at time T by the network, just because we need to have some arithmetic over here. So in this case, S0 is B, S1 and S3 are E, and S2 is F, right? At each node, I'm going to keep track of two things. Who was my best parent, and what is the best path score to the node? So if I start now in the first column, I'm going to say the best path score to every box except the very top left box is 0. So all the boxes which have been blacked out, they have 0 best path score. That's because there's no way the alignment can begin in those boxes. And the top left box itself, it has no parent. So its parent is null. And what is the best path score starting from the top left box to the top left box? It's just the top left box score itself. So that's simply going to be y0 times y0 as 0, right? That's just going to have its own node probability. And then I can go forward one column at a time. And so at this column, for each of these nodes, I'm going to find out who the best parent is. Which parent has the highest probability? For the top guy, of course, there's only one parent. So the best parent is simply going to be the 0th row itself. And the best path score is simply going to be the extension of the best path score to the best parent by multiplying in the node score. And so it's basically the best path score to the best parent times yt as 0. But for subsequent paths, if you go down, every node has two parents, right? I can find which parent has the highest path, the highest probability. And deciding, depending on whoever is the best parent, I'm going to store the information about who the best parent is, and then just multiply the probability of the best parent with the current node score to give me the best path score to the current node. I can do this for all of the nodes in my column. And I can keep doing this left to right. So because the first three nodes the first three boxes all have 0 probability, you'll find that the last two boxes in the second column, regardless of which parent you choose, are going to have 0 probability, right? But then you can just keep doing this left to right. And at each point, as you go left to right, what you will be doing is keeping track of which parent the best path came from and the probability of the best path to the node. That is the algorithm. I've sort of flown through this algorithm, but is this making sense to you guys? Right? Nothing is not at all complex. At each point, you're saying that the best parent is if the best path score so for the node at row L at time t, if the best path score to the node at row L minus 1, the previous row at time t minus 1. So, if you're here, if this guy had a higher probability than this one, then the best parent is just L minus 1. Otherwise, the best parent is L. That's the only information. That's the best parent information you're keeping track of. And then you're just multiplying the probability of the best parent with the node probability to get the probability of the best path to the current node. And then once you get all the way to the bottom, right, you've computed the best path scores to all the nodes in the graph. But then now you know that the best path must end at the bottom right corner, right? And for every node, you have kept track of where the best path came from. So you can track your way backwards and say, for every node, the previous, if I know which node was in the which symbol was in the best path at time t, I can just pick up its best parent, and that must be the symbol on the best path at time t minus 1. And I can work my way back and find the best path through the entire graph. And once I do this, I actually find an alignment, the most likely alignment of the symbol sequence to the input. Yeah.
I think maybe I'm missing something, but why couldn't we just take a more simple, like, greedy approach, and then at each time step you either go like straight and low or down?
If you took the most simple greedy approach, you might find that the greedy approach is not guaranteed to give you the best, most likely overall path. So for instance, you might find that at this node, in this row, maybe this guy is the most likely symbol. In this row, this guy is the most likely symbol. How do you maintain continuity? You cannot, right?
Right, but in that example, for example, what you wrote on the board, that like the third node at the bottom, if you go and the previous path has a higher probability, it's guaranteed that the next one.
Yes, but the problem is this, that out here, you don't know that this guy, the best path coming here doesn't have a higher probability, right?
Oh, okay, I see.
So you can't just be greedy about it. So you have to follow the whole algorithm through. Anyway, once you have the alignment, now you have a candidate alignment of the symbol sequence to the input. And so you can use that for training, but first you answer a poll. I know this loop sounded confusing, which means the poll will confuse you too. The Viterbi algorithm really deserves more time than that, but still. Okay. Someone on Zoom, is the first statement true?
Yes.
Sumesh, what about the second one? Also true. Marley's third one.
The third one, no.
Third one, no, right? The Viterbi algorithm does not select the most probable symbol at each time. You want to trace back from the bottom right corner, right? Yeah.
For the second option, how is the table of compressed sequence?
Is run on a probability. So the table, if you look at the rows what is at the left? That's the compressed symbol sequence that you have been given as your training label sequence, right?
If I go from, let's say, B, so compressed is just B.
So every path through this is guaranteed to compress to.
So we are looking at the compressed sequence vertically.
Yeah. So the horizontal sequences are time synchronous. They are expansions. And the vertical sequences, compressed sequence. So what we did was to create a table of compressed versus expanded, and then you found the best path through it. That's a good question, actually. Anyway, so just in case my explanation was not sufficiently confusing, I have some confusing pseudocode. Please look at it. But actually, it's not so bad. Now, so what happens is once you've done the Viterbi training alignment, you're going to get an alignment of the compressed symbol sequence to the input. And so now you're going to get an expanded sequence with one symbol at each time. So once you get a symbol of this kind, you can just use that expanded symbol sequence as your target. And now you can train your network. Yeah.
But like by using the algorithm, we are enforcing a model to construct a single output sequence that satisfies the order alignments. But like initially, the model is pretty much random.
We will get to that. That's a yes. Actually, it turns out that yeah.
So using Viterbi, this is our model output, right?
Uh-huh.
So now how do we compare it with, like what do we compare this with?
That's the, no, so the Viterbi gave you an alignment.
From the model's outputs.
It gave you an alignment of the symbol sequence to the input, right? And so now you're going to use that as your target sequence. And so when you use that as your target sequence, I'll answer your question in a few seconds, right? If you use that as your target sequence, you can define the divergence between the target sequence and the actual output of the network. And is that making sense? Does that answer your question? Right? So I'm going to assume that this alignment, I know this to be true, correct? This was part of my training data. I'm now going to assume that this is also true. And once I assume that this is true, then I can just write down my divergence, which is the sum of the negative of the sum of the log likelihoods, log probabilities assigned to the symbols at each time. And the derivative of this divergence with respect to the output at any time is going to be interesting. If you look at this divergence at time t, the divergence is only a function of the aligned symbol at time t. It's not a function of anything else, right? So the derivative of the divergence with respect to the output vector at time t is going to be 0 for all the components except the one symbol that was aligned to the input at time t. And so the derivative is going to be, and this is important, I need you to keep this in mind. So the derivative of the overall divergence with respect to the network output at time t is going to be a vector of zeros except for the one symbol that was aligned to time t, and that one component is going to be minus of 1 over the probability assigned to that component. Now, as you can see, this means that if you're performing gradient descent, because the derivative is negative, you're going to be trying to increase the y value, right? So you're going to keep pushing that probability higher. And now I can use this to train my model. And as all of you correctly pointed out, this seems like a bad thing to be doing. Why? If I have a properly trained model, what am I doing? I don't need to be training it further. What really happens is that I'm trying to build a model from my training data. So the way you would do it is guess some initial alignments and hopefully the initial alignments are not too horrible. Like Ritu mentioned way back when, if I have some idea of how long the various phonemes might be, my initial guess for the alignment might be heuristically set to something reasonable. More generally, you're going to pick something random, right? Then you train models with it. But then using this trained model, you're going to go back and realign all of your inputs. Realign the symbol sequences for all of your inputs. And then you can use those to go back and update your model and keep iterating this process. And each time the model is going to get better. There are different ways of doing it. You can just say, once I have my model, I'm going to align all of my data and then train my model, which would be very inefficient. But if you're using the SGD approach, then using the latest model, you'll be aligning the next batch of inputs that you're considering. And use those aligned inputs to compute your derivatives and update your model and use the updated model on the next batch. And that's probably going to be more efficient and effective, yes.
Professor, is there going to be ever a heuristic for alignment that we learn as well? Or do we just go one epoch, update the model, compare our alignments such that in the next epoch, we guess the alignments better?
So you can actually show that if you look at the total probability of your data, that's going to keep increasing. So you don't even have to go back and compare. You just have to say, remember, at each time you're picking the most probable alignment, right? So if you look at the total probability of the data, training is increasing the probability of the alignment. Alignment is increasing the probability of the alignment, right?
Yes.
So at each step, the probability of of your alignment is guaranteed to increase.
But we do alignment for every specific example.
Yeah.
So we cannot, let's say, use the example for, let's say, beefy for bat, right? Because if I understand that my alignment for beefy is wrong, I cannot use that insight to improve my alignment for bat because they're two different alignments that I'm guessing. So I have to wait the next epoch to improve the alignment.
So no, so the whole point is that the assumption here is that you're correct more often than you're wrong. And so across your entire training data, eventually you do the right thing, which is what we do all the time anyways, right? Yeah.
Okay.
So you're not making any assumptions at the individual level, yes.
So then, I guess, just to follow up on that, so the assumption that you mentioned, does that also mean that the length of your training data sort of affects the accuracy? Because like, I'm assuming the longer the alignment required, the more wrong you can be than right.
You're absolutely right, right? So we like to make those things shorter. If you have long, 5-minute long recordings, it's going to take a heck of a lot of time for your model to converge.
And that also means that you're, in essence, losing some of the location data when you're.
So if you have, so here's the crazy thing. We're going to talk about the forward-backward algorithm in the next class, which is a better way of doing things. But if you're a big company and you have the entire Amazon forest to burn, and you have enough data, you don't care. You just throw enough data and just use this algorithm, and the models turn out to be just fine.
How can that model even like converge? Because like this is different from the previous optimization problem. Like in previous optimization problem, because we have a ground truth label as a fixed stuff, so the always fixed. But here, like with as we like
Post it on Piazza because I'm running out of time, and I'll give you the math for why it works. Right? Make sure to post on Piazza. We should have a thread for today's lecture. That's a very good question. And we'll show you why it works, and we'll also explain why what we will be talking about in the next class also works, okay? So anyway, during SGS, the general idea is this. If my model were good, my alignment will be good. If my alignment is good, my model is going to be good. So the assumption we're going to make is that you're always reducing the loss. You're picking the alignment that has the lowest loss. Then given the alignment, you're picking the model that has the lowest loss, right? So every step is guaranteed to increase the loss. When you're finding the alignments, you're minimizing the loss because you're maximizing the probability, right? So if I follow a sequence of steps that always decreases the loss, what am I doing? This is a hill, valley descending algorithm, right? So this is going to find a local optimum. That's the basic idea. And if you have enough training data, eventually it will find a good local optimum. But if you don't have 1 trillion training instances and lots and lots of investors willing to throw billions of dollars at you, this is not a very good idea because it's going to be very heavily dependent on the initial alignment. And so it's prone to poor local optimum. If you're working with limited amounts of data, this will probably give you a bad model. And so in that case, what can we do? What we did over here in this process, in this algorithm, was to start off with an alignment, and then use the alignment to train the data, then use that model to train the model, then use the model to improve your alignment, and kept flipping back and forth. At each point, you were committing to a single alignment. You're saying, here's this alignment. This is what I believe to be the ground truth. And then you were optimizing your model to that alignment. What if you don't commit to an alignment? So you say, I'm going to try to optimize my model for every possible way of aligning the data to this model, or aligning the symbol sequence to this input. That's what you would do, right? So the iterative update problem, the approach is heavily dependent on initial alignment, prone to local optima. Here's the alternate solution that we will discuss in 48 hours, 46. How not to commit to an alignment, right? Next class. training without explicit alignment, which is the original CTC framework. And also, how do we deal with repeated symbols? Any questions? Yes.